In this lesson, we're going to cover Big Idea 4, Standard 5, and our topic today is intermolecular forces. So before we talk about what intermolecular forces are, we're going to talk about what they aren't. So we have something called intramolecular forces with an A. Intramolecular forces are the attractive forces within a molecule. Intra means within. When we're talking about intramolecular forces, we're talking about our bonds, our ionic bonds, polar covalent bonds, nonpolar covalent bonds. What are the forces that keep a molecule together? So our focus for this module are going to be intermolecular forces. Intra means within, inter means between. So intermolecular forces are going to be the attractive forces between molecules. So let's draw a picture and look at the difference. Let's say I had two water molecules. So there is an attractive force that is holding these hydrogens to that oxygen. And we call that an intramolecular force. The attraction within this molecule, that covalent bond holding hydrogen to oxygen, is an intramolecular force. What we're talking about today is going to be intermolecular forces. So if I had a beaker of water and there were a ton of water molecules in there, there is going to be a force that is going to hold those water molecules together, and we call that an intermolecular force. So let's go through the types of intermolecular forces. You should know the types. You should be able to identify the types in various molecules, and you should also be able to rank them according to their strengths. So IMF is just an abbreviation for intermolecular force. Up first are the London dispersion forces, or LDF. All compounds have London dispersion forces. So this one should be automatic. When you see a question that says list every intermolecular force, automatically put LDF. Every single compound has some LDF. If the molecule is nonpolar, LDF is the main intermolecular force. This is the main intermolecular force between nonpolar compounds. Well, why does this force occur? It has to do with the electrons. So we know that electrons are constantly moving. So let's say at a particular moment, part of the molecule may become more negative due to the distribution of electrons. Alright, so I know that was a lot. Let's draw a picture to explain what is going on. So let's say, here's my nucleus, and I have some electrons out here in the electron cloud. This image on the left represents a symmetrical distribution of electrons. But we know that these electrons are going to be constantly moving in the electron cloud. So let's say now at one point, as those electrons are moving, they all end up on one end of that atom molecule. This one would be an asymmetrical distribution. So what happens when we have this asymmetrical distribution is we are going to create what is called a dipole. Since electrons are negative and all the electrons are on this side of our atom, it is going to have a partial negative charge. I have no electrons over here, so it's going to create a partial positive charge. Remember, intermolecular forces are the forces of attraction between two molecules. So what happens is oppositely charged molecules momentarily attract. Causing, this is either caused it is either called a momentary dipole or an induced dipole. So let's look at what happens when this happens with two molecules. So here's my nucleus again. And let's say when those electrons are all moving, they end up on one side of that molecule. So electrons are negative. This side of the molecule is going to have a partial negative based on the distribution of electrons. No electrons over here, so it's going to be positively charged. If this happens with a neighboring molecule, we are going to have positive, negative, opposites attract. So there is going to be an attraction between these two molecules, and that is our London dispersion force. This opposition of charge is going to hold these two molecules together. But let's think about this. The electrons are not going to stay like this. The electrons are constantly going to be moving. So that means that this force is not permanent. It is momentary based on the distribution of electrons. So since this force only occurs when the electrons are distributed in a way that we can induce these dipoles, this is going to be the weakest intermolecular force. So we are going to increase in strength. So London dispersion, or LDF, is going to be the weakest. Moving up in strength, next comes dipole, dipole. We said LDF was for non-polar molecules. Dipole, dipole is the main intermolecular force between polar molecules. This one is going to be a little stronger. Since these molecules are polar, that means one side of the molecule is always partially positive and the other is always partially negative. Since we always have these two poles, we call this a permanent dipole. So in a polar molecule, one side of the molecule is always positive, the other is always negative. This is going to be a permanent dipole. An example would be hydrochloric acid, or hydrogen chloride gas. Chlorine is much more electronegative. Electronegativity is the tendency to attract electrons. Since it is much more electronegative, it's going to pull those shared electrons closer to it, creating that partial negative charge. The electrons get pulled away from hydrogen, so hydrogen gets the partial positive. Again, intermolecular forces are occurring between different molecules. If you were asked to draw where is the intermolecular force occurring, again, opposites attract. The reason these two molecules are going to be held together is because that partial negative chlorine of one molecule will be attracted to the partial positive hydrogen of another. This is my intermolecular force. Since these molecules are polar, it's going to be a dipole force. LDF is the weakest. This one is going to be a medium strength intermolecular force. Lastly, hydrogen bonding. Hydrogen bonding is a type of dipole-dipole force. This is a special dipole-dipole force that occurs between hydrogen and it has to be a small electronegative atom. So this occurs between hydrogen and either fluorine, oxygen, or nitrogen. This is going to be a very strong intermolecular force. All right, so let's do some practice. Let's say you were asked to determine all intermolecular forces acting on two molecules of, first one, let's do water. So the first thing that we have to do is draw the Lewis structure. Next, we need to determine the polarity. Because remember, intermolecular forces depends on polarity. So water, H2O, has lone pairs of electrons on that central atom. This molecule is going to be polar. Let's determine all of the intermolecular forces acting on it. So up first, every single molecule has some London dispersion forces. Molecules that are polar also have dipole. Hydrogen bonding occurs between hydrogen and oxygen. Our three options for hydrogen bonding are oxygen, nitrogen, or fluorine. So water also has some hydrogen bonding. This one would have all three. Let's try methane, CH4. So again, step one, we need the Lewis structure. The reason we need the Lewis structure is because we cannot figure out our overall or molecular polarity without the Lewis structure. Look to see, is this molecule polar or nonpolar? This one is completely symmetrical. Look at all of carbon's attachments. They are identical. That makes this a nonpolar molecule. Every single molecule has some London dispersion forces. If it is nonpolar, LDF is its only intermolecular force. So your only answer for B would be LDF. Let's do one more. So step one, draw the Lewis structure. Step two, based on your Lewis structure, determine, is this molecule polar or nonpolar? I see a lone pair of electrons on the central atom. This is a polar molecule. Lastly, let's figure out our intermolecular forces. Every single molecule has some London dispersion forces. If it's polar, it also has dipole-dipole interactions. Lastly, is there any hydrogen bonding? Nope. Hydrogen bonded to either nitrogen, oxygen, or fluorine. So I do have nitrogen, but it is not attached to a hydrogen, so this molecule would not have hydrogen bonding. Its intermolecular forces would be both LDF and dipole-dipole.